Hello everyone, my name is Nabil and today I am going to present my research work titled Investigating Inconsistencies in PRNU-based Camera Identification. This work was developed at Politecnico di Torino under the supervision of Professor Bianchi. Camera identification is one of the crucial applications of digital image forensics. The aim of the camera identification is to verify the origin of an image and check its authenticity. A typical source identification problem consists of a set of reference cameras and a test picture, and the aim is to associate this test picture to one of the reference devices. Now, there are many methods that aim at identifying the origin of an image. However, PRNU-based camera identification prevails over the others. Every camera sensor is made up of millions of photosites, also known as sensor elements. The job of these photosites is to convert incoming photons into voltages. Ideally, these photosites should output equal voltages. However, because of manufacturing imperfections, these photosites output slightly different voltages with respect to each other. This leads to the deviation from the ideal response, and this deviation is known as photoresponse non-uniformity. PRNU, otherwise known as pattern noise, is considered unique to a sensor. Therefore, PRNU patterns of two different sensors are strongly uncorrelated. Moreover, this pattern does not depend on environmental conditions like temperature, humidity, etc. Above all, this pattern survives most camera processing. Therefore, PRNU is widely used as evidence by various law enforcement agencies in manipulation detection, image authentication, etc. However, recently smartphone cameras are undergoing tremendous amount of software advancements. According to a recent report, more than 85% of the world's pictures are captured by smartphone cameras, thanks to the computational photography, which has made possible the introduction of features like portrait, AI, HDR, etc. However, these features require a lot of in-camera processing, and the question arises whether PRNU survives such a complex in-camera processing. Is PRNU for modern devices unique and reliable? Our focus is to investigate robustness of PRNU in modern smartphones. Now, prior introducing the problem, we focus on the prerequisites. The PRNU is estimated in the following way. We take the original photo and subject it to a denoising filter. What we obtain is known as a denoised image. We subtract the two to obtain the noise residual. The idea is to suppress the image content and expose the pattern noise. Finally, we demodulate the noise residual with the image content to get the fingerprint of the device. In practice, several flat field images are used to estimate the fingerprint of the device. However, in our case, we used only one image to estimate the fingerprint of the device because we wanted to know whether the underlying problem is picture specific or not. In order to conclude whether the test picture was taken by one of the reference devices, we use two strategies: pairwise fingerprint comparison and pairwise noise residual comparison. Under pairwise fingerprint comparison, we correlate the fingerprint of the test picture with each of the PRNU references. We can do the same for the noise residuals as well. Now, in order to estimate the similarity scores of the two fingerprints or the two residuals, we use two correlation metrics: normalized correlation and PCE. Normalized correlation is simply the cosine of the distance between the two residuals or the fingerprints, while PC is the ratio of peak energy of the residuals to the average energies. These metrics are then compared against the threshold, and if the metric surpasses the threshold, then the test picture was likely taken by the one of the reference cameras. Ideally, PRNU pattern is quite unique to a sensor. Therefore, PRNU patterns corresponding to different sensors, even if belonging to the same camera model, same smartphone model, are strongly uncorrelated. However, what happens in the modern smartphones is that PRNU patterns corresponding to different devices of the same smartphone model exhibit increased correlation metrics. That is, they are no longer unique to a device. Rather, PRNU patterns of different devices collide with each other. This represents a problem given the usage of PRNU as an evidence in police investigation. In such a case, camera identification cannot be performed reliably. This problem was recently highlighted by Giuliani and his team. However, no solution exists to counter the problem. We believe that the problem of fingerprint collision occurs due to introduction of non-unique artifacts in the images of modern smartphones. The computational photography The processing associated to the computational photography is likely to be similar between different devices of the same smartphone model. Therefore, different devices belonging to the same smartphone model suffer from the same non-unique perturbation. We believe that these non-unique artifacts only affect a fraction of images, and those images which suffer from the non-unique artifacts, we call them bad images. These bad images have an extra term epsilon in their PRNU model with respect to the PRNU model of a good image. This epsilon refers to the contribution due to non-unique artifacts associated to the computational photography. This epsilon is common to all images from same camera model. Thus, if we think of correlating PRNU fingerprints or the residuals corresponding to two bad images belonging to different devices from same camera model, we expect to see a correlation value greater than the threshold due to the common epsilon, due to the collision of non-unique artifacts. In other two cases, when we correlate two good images or one good and one bad image corresponding to different devices, we expect to see a correlation value less than the threshold due to no element of similarity. Only when we correlate two bad images, we expect to see a correlation value greater than the threshold due to the common term epsilon. Thus, we expect to see a bimodal distribution with one mode with usual zero mean of non-matching fingerprints and another mode with a higher mean. We propose methods to identify images suffering from these non-unique artifacts. Our dataset consists of images from recent smartphone models. Since these smartphones feature pixel binning, it is possible to shoot pictures at different resolutions. For each resolution, we have certain number of devices, and for each device, we have close to 70 pictures. We analyze the problem between different devices within the same resolution from the same camera model or smartphone model. For the sake of time constraints, we only show results corresponding to pairwise noise residual comparison. However, same holds for the pairwise fingerprint comparison as well. These correlation values, these histograms depict correlation values corresponding to the Samsung models. X-axis represents the correlation value, normalized correlation value, and the Y-axis represents normalized frequency. A pink line indicates the detection threshold. Ideally, we expect to see correlation values less than the threshold. However, as you can see, a lot of correlation values surpass the threshold for each of these Samsung models. These correlation values which surpass the threshold are a result of correlations between bad images only as exposed by our model. On the other hand, for the Huawei models, the problem is not as significant as the Samsung ones. Notably, for the highest resolutions of the Huawei models, none of the pairwise correlations surpass the threshold. Therefore, there are no bad images for these two models. We thoroughly probed metadata settings and tried to link these settings with the unexpected behavior. However, we could not find any link between the standard metadata settings and the unexpected behavior. The same value of ISO or the exposure could result in a correlation value greater than the threshold or less than the threshold. This slide reveals the validation of our model. By validation, we mean number of times correlations between bad images actually results in a correlation value greater than the threshold. We also introduce a margin, a sort of a relaxation for our model, and we consider a bad image as bad if it's included at least in margin number of bad correlation values. The rationale is that this margin number is small, let's say 7, and for the sake of validation of our model, those images can be considered as good. As you can see, our model makes sense for these Samsung models, for these Samsung smartphones. The validation percentages are pretty high. However, for Huawei model, the validation percentage is very low. This is because our model assumes only one class of bad images suffering from the same non-unique artifacts. And in practice, there might be several class of bad images suffering from different non-unique artifacts. Nevertheless, our model, though simple, explains the cause of unexpected behavior for these Samsung models, for these Samsung smartphones. Since our methods aim at identifying good and bad images, we need a basis to validate the performance of our algorithms. We manually identify good and bad images for each of these Samsung models and the Huawei ones. As you can see, for the highest resolution of Huawei models, None of the pairwise correlations exceeded the threshold as already seen. Therefore, there are no bad images for these models. Our first algorithm is based on the presence of scene type tag in the metadata settings of the image. We find that those images which contain scene type, a directly photographed image, resemble good images. That is, none of the corresponding pairwise correlation values surpass the threshold. On the other hand, those images which do not contain scene type resemble bad images. Therefore, absence of this tag can be linked to the presence of non-unique artifacts in the images. This slide shows the validation of the scene type classifier. This histogram shows the distribution of correlation values, distribution of pairwise correlation values for those images which contain scene type in green and for those images which do not contain scene type in black. As you can see, for the green histograms, the correlation values are less than the threshold. Almost all of the correlation values are less than the threshold. While as for black histograms, the correlation values follow a bimodal distribution. Therefore, scene type tag can be used to separate good images from the bad ones. This confusion matrix reveals the accuracy of the scene type classifier. The classifier achieves very decent accuracies in correctly identifying good and bad images. However, this classifier applies to Samsung models only. Our second method is based on spam features. Spam features capture dependencies between the pixels of an image. Since in a bad image, the dependencies between pixels are modified, therefore spam features should be distinct for good and bad images. However, spam features are high dimensional for an image. Therefore, we need to resort to PCA prior training the classifier. The classifier is then trained to learn the features corresponding to learn the spam features corresponding to good and bad images. This confusion matrix reveals the accuracy of the spam classifier. The classifier achieves very high accuracy in correctly identifying good and bad images. However, it needs exact camera model for training. Overall, we verified the problem of fingerprint collision in modern smartphones as exposed by Giuliani and his team. We introduced a model of non-unique artifacts for bad images that explains the unexpected behavior of PRNU in modern smartphones and successfully validated the model on our data set. We could not find any link between the metadata settings and the unexpected behavior. And finally, we proposed two methods to identify images suffering from non-unique artifacts. Our methods could be used to single out images suffering from non-unique artifacts to exclude them from a set used to compute fingerprint or giving low confidence to them, to low confidence to tests involving them. Thank you for your kind attention.